Okay, welcome to our last lesson in equilibrium. The good one. So buckle up, get a calculator. So get a calculator and please try to follow along with some of these. So definitely this is one that you're going to want to pause and try and complete on your own and then rewind and so on. Just to try and watch some of these calculations using that equilibrium constant. Some of the questions quite straightforward, some a little more involved, okay? So there's a few different types of calculations that will involve KEQ. The first one, don't worry about memorizing the type numbers or anything, just sort of a general categorization. So the first one, when you're actually finding or calculating the KEQ value. So in this type of question, I'm going to give you the equilibrium concentrations. So this is going to be kind of as straightforward as it gets, okay? So here's a reaction given to you. It's balanced, okay? And you're going to be given some information. So at equilibrium, and you're given these concentrations. So you're given the concentration of your reactant and all of your products. Calculate KEQ. So I've got my answer here. I didn't mean for it to show up, but it's sitting there. This is my final answer. Notice there are no units at all. Okay, it's just the value there. And this is giving me a ratio of the products to reactants for this equilibrium at this given temperature. So this value of 0.5, it's less than 1. So it tells me that my product concentrations divided by my reactants, if it's giving me a value less than 1, then my products are lower than my reactants in general, okay? To calculate this, really straightforward. First, write out your equation. Oh, not showing up. There we go. First, write out your equation. Okay, so that would be like from the last lesson. Now, this one, we should probably do a harder example, but this one, notice all of my coefficients are 1. So I don't have any exponents to worry about in here. Be careful that if you did, careful to include, those coefficients as, square, cubed, etc. I'll just say if needed. We don't have any in this one as my coefficients are 1, okay? Write out the equation. So I always want to see you write out the actual equation without any numbers in it. And then plug in your numbers, just making sure you plug them in the right spot. So plug in your concentration for each of these species given to you. Now I can go directly in here because it told me I was at equilibrium. So that's a really important statement. Since I'm at equilibrium, I can use my equilibrium constant because that's when that's true. Plug in your values and calculate. So in this case, 0.4 times 0.4 divided by 0.32. This is the stage where if you did have anything that was squared or cubed, you would just be really, really careful to do that to the numbers that were needed. So in this case, I end up with 0.50. Notice I've kept 2 sig figs because that's what I was doing. 2 sig figs times 2 sig figs divided by 2. Okay, that's my answer. KEQ equals 0.50. Second type of question, a little bit more involved. Same approach, just means solving takes maybe a couple more steps. So here's an example. There's a reaction given to you. Balanced equation is done. Notice the difference here is I've actually given you the KEQ value. The KEQ value under whatever conditions we're talking about is 625. So again, just for practice, you don't need to here, but what does that help me understand about the relative amounts of my products to reactants? I've got lots more of the products than I do of the reactants because that division is giving me a number like 625. So calculate the hydrogen concentration. If at equilibrium, the nitrogen concentration is 0.030 molar and the ammonia concentration is 0.12 molar. Okay, so first step's always the same. Get your balanced equation, which we've got. Write out your equation. Okay, so notice my equation here. I do have some squareds and cubes to worry about. So product concentration raised to the power of 2 divided by, I got two reactants, they're both gases, so I include them. Hydrogen concentration cubed multiplied by the nitrogen concentration, okay? The order here, sorry, I should point out, the order here doesn't matter. So I've written that in kind of, I would have written this normally on the bottom, just because that's the order they are in the reaction, but they're both fine. They're both in the denominator here, so we'll get the same answer. Okay, plug in your numbers. So plug in your values, and we get this. Now notice the big difference between the last question is we actually have the KEQ value given to us. So I plug that value in this time. On the right-hand side, we're missing something. We're missing this, hydrogen concentration. So we got a bit of work to do. Now, to solve this, this is like any question in math where you got some value, some rational expression, you got a missing x that you got to solve for, right? Solve it like that. So, I mean, I do kind of expect that you can solve that if you need to pause it and kind of try it on your own, and it's certainly not a bad idea, okay? If you're doing this one, what I'd probably do is I'd probably simplify this down. So 0.12 squared is going to get 0.0144. On the bottom, I've got my hydrogen concentration cubed. If you want, you can throw an X in for that, but there's no point. Just leave it as that sign, that symbol there, divided by 0.030. On the left-hand side, 625. It's up to you where you go from here. If you want, you could certainly simplify down the right-hand side a little bit more, right? You could divide those if you like. You really don't have to. Okay, so 0.0144 divided by 0.03. I get 0.048. Now notice on the bottom, I still have this hydrogen concentration cubed. It's still there, hasn't gone anywhere. So now I got to simplify this down. It's up to you again where you go from here. You could rewrite this as, do some rearranging or cross multiplying. You could get this. So that 0.048 divided by 625. I get 0.0000768. Now the big kicker here is we can't forget to do something, and that's we cannot forget that this is cubed right now. So I got to cube root this, both sides. And I get my final answer, my hydrogen concentration, if I cube root that decimal over there. Okay, so if I do that, I get, so just hidden here, I get 0.092. Now notice there are units, because that's a concentration. So I've given units of moles per liter there. That's my final answer. So this one, to solve that, if the math threw you off, then you just got to practice solving for that unknown. In this case, in the bottom, because it was a reactant. Okay, but a few steps involved there for sure. Okay, so now it's going to get a little bit even more involved in that. So a lot of times we're not given information at equilibrium. We can't jump right to equilibrium, constant calculations, unless we actually have those values at equilibrium. So if we're given information about initial or starting concentrations before a reaction has reached equilibrium, we need another approach. We need a method that's going to help us figure out the changes that occur to reach equilibrium. So we're going to use the best way to approach this is what we call the ice table method. You hear me talk about ice tables all the time. And that's going to help us keep track of the I stands for the initial or starting concentration at the beginning. The C is the change in concentration. How much do things go down by or go up by as they react? And the E, hopefully obviously, is standing for the equilibrium concentrations. So we're going to make a table for a reaction that looks something like this. Now on the left-hand side, you're going to keep track of your initial concentrations, your changes of concentrations, and your equilibrium concentrations in that order. Along the top, you're going to keep track of your reaction. Literally just rewrite your reaction. So write it out really neatly. Give yourself kind of a column for each species here. Keep really clear track of where your reactants are to the left and your products to the right. So to fill this out, you're going to take any information they gave you in the question. You're going to fill in what you can. And you're never going to be able to fill out the whole table. Don't worry about that. In the top row, you're going to fill in any initial or starting concentrations that they might give you in a question. The second row is usually one that you need to do some figuring out on your own. And this is going to show how much the concentrations actually change by. So if things go down, we indicate that they, minus whatever. If they increase concentrations, we say, plus a certain amount, that sort of thing. Okay. This row is a really important one because when things are changing, that's when your reactions actually happen. So it's really important that the numbers in this row obey the mole ratios in your equation. Okay. So for example, in this reaction, in this example, I know that the numbers in these three boxes, whatever they are, must follow this 1 to 3 to 2 ratio to each other, okay? And that's really super important when you're filling out that row. The last row is just the final or equilibrium concentrations. So that's when the reaction has reached that balance of equilibrium and those concentrations stop changing. So let's look at an example. The point here is really important. Always use concentration. So it's got to be molarities in that table. So here's an example here. Find the equilibrium concentrations or KEQ, depending on what they ask for, when we're given some initial and some equilibrium information. So we're kind of given a mix of a bunch of information. So here's an example, same reaction we saw before. The question is, we start off with 0.32 moles of nitrogen and 0.66 moles of hydrogen in a 1 liter flask. So that's important there. At equilibrium, the hydrogen concentration is 0.30 molar. Find the equilibrium concentrations of the other two species, the nitrogen and ammonia. So start off with your table. Label it. So initial concentration, change in concentration, equilibrium concentration. Fill in your reaction along the top. Make sure you fill in the balance reaction. Now notice the ratio here is 1 to 3 to 2. So those coefficients will be really important at some point. Okay, so now we just fill in whatever we can. Okay, so let's look at the question at the top. Let's look at what they told us. They told us that 0.32 moles of N2 and 0.66 moles of H2, the hydrogen, are put in a 1 liter flask. So they didn't give me concentrations, but they made it pretty easy on me. They did tell me that I'm in a 1 liter flask. So, I mean, you can do the calculation if you really need. It's pretty straightforward. 0.32 moles divided by 1 liters is just 0.32 moles per liter. So, and that's what we start with. So that's what's put into the flask at the beginning. So 0.32 molar is what I start with for nitrogen. Let's do the same thing for hydrogen. 0.66 molar is what I start with for hydrogen. What do I start with for the ammonia, NH3? I don't start with any. I have none at the beginning. They told me what I started with, and that was the nitrogen, hydrogen. So what's my concentration of that product at the beginning before that reaction is really going? It's just 0. Okay, I have none. So that 0 is important though, so fill it in. So let's keep going. At equilibrium, the hydrogen concentration is 0.30. So that's way down here at equilibrium of 0.30. Okay. Find the equilibrium concentrations of the nitrogen and ammonia. That's what I'm after for my final answer. Now you got to do a little bit of detective work here, a little bit of figuring out what's actually going on. So first thing I would look at is this row right here, because there's enough information there to figure out what happened, what changed. I started off with 0.66 moles per liter of my hydrogen. I somehow finish, I end with 0.30 moles per liter of that hydrogen. So obviously that's gone down, that's a decrease. So I'm going to put negative to decrease, and it's a change of 0.36 moles per liter. Okay, so start with the column there that you have two things for. You have enough information to figure out that missing box. Okay, so now it gets a little bit more figuring out. So now I can jump over to one of these other changes here. Now here's where you got to be very careful with your mole ratios. Okay, looking at the reaction we had, I'm just going to highlight this. Looking at the reaction above, we have a 1:3 ratio for my nitrogen and hydrogen. Okay, so it's really, really important that these amounts in this middle row follow that ratio. So for example, it can be 1 and 3, it could be like 100, 100 and 300, right? It could be 0.1 and 0.3. Whatever they happen to be, they have to follow that ratio. So let's think backwards here. This is 0.36, which means this is 0. Now, going from a ratio of 3 to 1, I'm going to divide by 3. So 0.36 divided by 3 is 0.12. So these two values now obey that ratio in the coefficients of the balanced equation. The other super important piece is the sign here. What sign are we going to have in front of this? Is that positive or negative? And it's really important we catch that it's also going to be negative because it's also a reactant. So if hydrogen's a reactant being used up, and it's going down by 0.36, well, my nitrogen's also a reactant, so it's also being used up and going down, decreasing its concentration. Okay, I can actually finish this row, or pardon me, this column. 0.32 is what I started with. I'm decreasing, negative, so decreasing by 0.12. So my final nitrogen concentration is 0.20 molar. The far right-hand side, I'm going to do the same approach. So now notice the ratio here. I've got a couple options here. Okay, I could start with my 0.36 and try and figure out what this is going to be. That usually gives people more problems. So it's definitely doable. So nothing wrong with it at all. It's just a mole bridge. But it's usually easier for people to start with the one that has a 1 in front of it. So if this is 0.12 and its coefficient is 1, well, what is this ammonia going to be like compared to that? And it's going to be double. It's a 1:2 ratio. Okay, so whatever the nitrogen is, I've got to double it for the ammonia. So double this one, and it's going to be 0.24. Okay, now again, what's the sign? And it's really important that we understand this is going to be an increase, a positive change. Okay, it's a couple, it can't go down. You had 0 to begin with. Okay, but the reason it's the opposite sign is it's on the opposite side of the reaction. Okay, if these reactants are being decreased, they're being used up. This is a product over here, so it's going to be increased. It's going to do the opposite change. To finish this column on the right-hand side, I just do the math. I started with 0. I increased by 0.24, so the math's easy, just finishes at 0.24. Okay, so what I could do now is I can answer that question finally. Question asked for the nitrogen concentration at equilibrium. So I would just write my final answer very clearly. I've already got it in the table, and then same for ammonia. Equilibrium 0.24. Okay. Another question they might ask you is they might ask you to actually calculate KEQ. If you had to do that, then you would just stick these numbers into the equation that you'd write out, like a question from our last lesson. Okay. Okay, our next one. This, if you thought that one was big, this one is bigger. So this is going to test your math skills a little bit. Okay, same approach as the last one. So a mixture of 0.500 moles hydrogen, 0.500 moles iodine is placed in a 1 liter flask. At equilibrium, the KEQ is 54.3. So it's given to us. We got our reaction given to us as well. Okay, so we're going to start with our table. So you want to write that out. Write out your ice table. Write your reaction along the top, keeping real nice, neat track of everything. And then we're going to fill out what we know. So let's fill out what we know. So again, we're given the moles amounts, but we're in a 1 liter flask. So that makes life a little easier. I just divide by 1. So 0.500 molar. My iodine, also 0.500 molar. How much hydrogen iodide do we start with? None. What else do I know? At equilibrium, the KEQ is 54.3. Now this question all of a sudden got way different than the last one because I don't know anything else in this table. That's the only information they gave us. So this is definitely making things a little bit trickier. Okay, so we're going to have to approach this in the same way, but it's going to definitely turn out quite different in a second here. So let's think of what we do know. Well, we start off with some of our reactants and no products. So what's going to happen? Well, my reactants are going to react together and start to form some product. Okay, so what I do know is that I'm going to use up some of my reactants. I don't know how much yet. So I do know the sign in there is negative. I know that the change for these reactants is going to be negative because some will be used up. Okay, and that's true for my iodine here as well. Okay, what do I know about this product? How is it going to change? Well, if some of my reactants are being used up, then that means some of this product will be formed. So how is its concentration going to change? It's going to increase. So it's going to be a positive change, okay? Next thing I got to worry about is what do I actually put in those boxes? Negative what or positive what? So here's where it gets a little bit strange compared to the last one, okay? In the last one, we had actual numbers we were dealing with. Here, I don't know numbers, but I really need something there. So I look at my reaction. I look at my balanced reaction. And I'm going to highlight the coefficients here, even though I don't write the ones. I'm going to write them. This is a 1 to 2 ratio here. So I do know that whatever's in this row follows that ratio, but I don't know numbers. So when I get to this point and I'm stuck and I have no more numbers, I start to use a variable to help me fill this information in. So I'm going to call this, I'm going to call this change for hydrogen X. You can use whatever variable you want. It's totally up to you. X just being more common. So that change is now negative X. So it's down by some amount X. For my iodine, it's a 1-to-1 ratio. So it goes down by the exact same amount. Whatever this went down by, This is the exact same. What about my product, HI? We've already decided it goes up. It's positive. Look at the ratio really carefully. It has a coefficient of 2. So whatever this hydrogen was, however much of that gets used up, I should be producing double the amount of HI. So if this was X over here, this I'm going to have to call 2X. It's double X. Okay? So now we can't actually complete, but we can sort of partially complete our table here. Okay? My equilibrium concentration for H2, the hydrogen, I'm now going to be able to write as 0.500 minus X. That's all I can do right now, is just say that it's started off at 0.500 and it went down by X. I do that for iodine as well. For the product, the hydrogen iodide, started at 0. I added 2X. If you want, you can write 0 plus 2X, but obviously that just simplifies to 2X. So I get these expressions for the concentration. I don't know numbers yet, but I know the expressions for them, okay? So now I'm just going to rewrite out my equation here because it's on the last line. I'm going to do the calculation. So now my KEQ equation, write that out very carefully. So that's your product concentration. Now notice that one has to be squared, divided by my reactant. So hydrogen, H2, no exponent there to worry about, multiplied by iodine. So always write that out first. Now fill in what you know. Okay, so if we just quickly flip back here, don't forget I gave you the KEQ value. So 54.3. On the right-hand side, here's where it's just going to get a little more difficult to solve. When I'm plugging in my equilibrium concentrations, I'm not plugging in nice simple numbers, I'm plugging in these expressions. So from the table, my HI I had as 2X, and that needs to be squared in this equation. On the bottom, I've got concentration at equilibrium for the hydrogen, the H2, at 0.500 minus X, and the iodine also at 0.500 minus X. The fact that those are the same is not a coincidence. It's because I gave you an easier one. This could be harder. I know you probably don't believe me, but this is going to allow us to simplify things down. So what I would suggest here, what I would suggest is on the right-hand side, simplify this or rewrite it, because the fact that those are the same allows me to write it as this, 0.500 minus X squared. Keep this on the left. So now I got to solve here. My goal here is I'm trying to solve for X. And the reason for that, if I flip back, if I can figure out what X is, then I can figure out what to subtract here, what to subtract here, and what to double there to get my final answers, okay? So that's my whole goal, is to try and figure out what the heck X is, okay? So solve for X. You got a choice to make. You can take the easier route or the hard route. The harder route would be to expand out your brackets, basically FOIL this out. You're going to be dealing with a quadratic, and then you're going to have to solve that quadratic for X. It's definitely doable, but don't do it. It's not worth your time. The simpler route, still takes some work, is to recognize that because I've got something squared on top, something squared on bottom, the quickest way to simplify this is to square root that rational there, as long as I square root both sides. So that's definitely the quicker route, and that's where we'll go. Okay, so on the left-hand side, if you want to be exact, leave it as root 54.3. Okay, if that throws you off and it kind of scares you a little bit, you can square root it and just round. Just don't round too much. So for example, in this case, 7.36, we can round that to 9, that sort of thing. Keep a few decimals. The reason we square rooted is because on the right-hand side, this now simplifies this. Okay, next up, we're going to multiply. You got some options, but my advice would be multiply by that expression on the bottom, because then you can just get rid of it there on the right-hand side. Now, on the left-hand side, just be really careful when you're multiplying into that binomial, that you distribute it. So on the left-hand side, I'm going to get 3.6845, let's go there, minus 7.369x. On the left-hand side, bottom's canceled, so I just have my 2x. Okay. I'm going to keep solving for x. Again, you got options. I'm going to add 7.369x to both sides. Sure up here. So on the left-hand side, I got 3.6845. On the right-hand side, I now have 9.369x. And finally, I can divide both sides by 9.369. All of that was just to get x. So I get, what do I get here? I get 0.393. Now, that's not my final answer, but I'm almost there. Trust me, I've done most of the work. So I'm going to flip back here. Remember that number, 0.393 for x. So if I flip back, I now know that I can do 0.500 minus 0.393, and I get 0.107. Same thing for the iodine, 0.107. For the hydrogen iodide, I need to double that. And I get, so 2 times x, that was the expression, so 0.786. So my final answer, I would write out really clearly, it asks for equilibrium concentration. So you've already got the answers, it's just good practice to give your final answers really clearly, especially give units. So 0.107 molar, 0.107 molar, 0.786 molar. And there's my final answer for all 3 equilibrium concentrations. If you want, you could test this. We can look at that together in class just to check our answer. Last one here. This is much shorter. Please don't worry, the last one is as hard as it's going to get. So this question here, what you're having to do is you're trying to answer which way will an equilibrium shift. So you're given some concentrations, and you're given an equilibrium value, constant value, and you're just asked, will the equilibrium shift to the right? Will it shift to the left? That sort of thing, okay? So what we're going to do is we're going to basically do our calculation for KEQ with the initial concentrations, okay? So we're going to call this number we come up with the trial KEQ. And the only reason we call it the trial KEQ is because we don't know if we're at equilibrium yet. We're just trying to see where we are, okay? The results we come up with, if the trial KEQ we come up with is less than the actual, then my reaction is going to shift to the right. Now, the reason for that is if your trial KEQ, when you do this calculation, comes up to be too small, you need it to be bigger. How do you get this ratio to be larger? Well, you need more of these and less of these reactants, okay? If your trial KEQ comes out to be larger, then it's going to shift the other way. So that's the opposite. If your trial KEQ, your little test kind of constant here, is too large, how do you get it to become smaller? So you need this ratio to become smaller. So you need less products, more reactants. That's a shift to the left. And there is a chance that your trial KEQ that you attempt is already equal to the equilibrium constant. So if it equals the equilibrium constant, you're already there. You're already at equilibrium. And there's no shifting that needs to occur. So let's test one out. The calculation's really quick. So here's an example given to us. KEQ is given to us. That's the actual equilibrium constant. And we're asked, how will the equilibrium shift? So to answer this question, we literally just need to say, our final answer will be to the left, the reactant side, or to the right, or no shift at all, okay? So the initial concentrations are given to us. So all we have to do is write out the equation, write out the KEQ expression with any squares or anything needed, plug numbers in, do your calculation. So this I should actually label, so make sure you call it the trial KEQ. So my trial KEQ is 5.0. Let's compare that to the actual. So my products divided by reactants is 5, but it needs to be 10. It should be 10 under these conditions, is where the equilibrium actually lies. So I need this to become larger. How does this get bigger or larger? Well, we need a larger number on top, so more products. We need a smaller number on bottom, so less reactants. So that's going to be a shift to the right so that we increase because of the sizes of those, okay?